Physical Chemistry, Chapter 4. We're beginning Section 4 now. We're going to talk more about the Gibbs and Helmholtz functions that we defined earlier in this chapter. Now first we're going to talk about constant temperature and volume. Since we're at constant temperature, the differential of temperature is equal to 0. Since we're at constant volume, the differential of volume is equal to 0. Now remember, the differential of internal energy is less than or equal to temperature times the differential of entropy plus the differential of work. Now we can add 0 to something, so you'll notice S dt minus S dt is equal to 0. So we're going to add 0 to this equation and get du is less than or equal to TdS plus TW minus S dt minus S dt. Now we can combine this TdS minus S dt, that's the exact differential for dTs. So we have dTs plus, is equal to S dt plus dTs. Oh yeah, we said that. It's an exact differential. So that gives us the differential of internal energy is less than or equal to dTs plus dW minus S dt. Now we're just going to move that over to this side, so we get the differential of the internal energy minus the differential of temperature times entropy is less than or equal to the differential of work minus entropy times the differential of temperature. Now we can combine these terms, so we can say the differential of U minus TS is less than or equal to dW minus S dt. Now remember, work, when we have PV work only, is minus PdV. So we have the differential of internal energy minus temperature times entropy is less than or equal to minus pressure times the differential of volume minus entropy times the differential of temperature. Now we said we're going to be at constant volume, so the differential of V is equal to 0. And we said we're going to be at constant temperature, so the differential of temperature is equal to 0. Which means this whole right side is equal to 0, so the left side must be equal to 0 too. So that gives us that the differential of internal energy minus temperature times entropy is less than or equal to 0. So we're going to define this Helmholtz free energy, capital A, is equal to U minus Ts. So A is called the Helmholtz function, which is a type of energy. The differential of A, therefore, is less than or equal to 0. Now remember, this is only because we're at constant temperature and volume. So isothermal and isochoric. We're also at thermal and mechanical equilibrium, and the only work is pressure volume work. Now remember, it would be equals when at equilibrium, or less when you're not at equilibrium. Now remember, mechanical equilibrium is also material equilibrium. So now, what if we have a constant temperature and pressure? This is actually more important. This is more like a lot of real-world experiments and so on, industrial processes. So we have the differential of temperature is equal to 0, and the differential of pressure is equal to 0. So we have the differential of internal energy is less than or equal to temperature times the differential of S plus the differential of work. So that gives us, we're going to do the same thing we did before. We're going to add 0 and we're going to add 0. So we have the differential of internal energy is less than or equal to temperature minus the differential of entropy minus pressure times the differential of volume plus entropy times the differential of temperature minus entropy times the differential of temperature plus volume times the differential of pressure minus volume times the differential of pressure. So that, let's see, what did we do here? Anything at all? No. Well, so we have du is less than or equal to TdS plus S dt. So we just changed the order around a little bit. Minus PdV minus VdP minus S dt plus VdP. So remember, this will be equal to dTs. This will be equal to dPV. So we equal to the differential of the internal energy is less than or equal to the differential of temperature times entropy minus the differential of pressure times volume plus volume times the differential of pressure minus entropy times the differential of temperature. So combining those on the left side, we get the differential of internal energy plus pressure volume minus temperature times entropy is less than or equal to minus entropy times differential of temperature plus volume times differential of pressure. Now remember we said we're at constant temperature, so dt is equal to 0, so this term is equal to 0. And we said we're at constant pressure, so the differential of pressure is equal to 0, so this term is equal to 0. So this whole right side is equal to 0, which means the whole left side is equal to 0. So we get the differential of internal energy plus pressure volume minus temperature times entropy is less than or equal to 0. Now we're going to define, remember an equal sign with 3 lines like that means always equal to. So enthalpy is always equal to internal energy plus pressure volume. So substituting that in, we get the differential of enthalpy minus temperature times entropy is less than or equal to 0. And of course the enthalpy, temperature, and entropy are all state functions. Therefore, enthalpy minus temperature times entropy is also a state function. So we're going to define G, capital G, remember equal sign with 3 lines means always equal to, G is equal to H minus TS. So we can say from that, substituting in, that the differential of the Gibbs free energy is less than or equal to 0, only if you're at constant temperature and pressure. So capital G, we're calling that the Gibbs free energy function. This is a very important state function. Now G, of course, is extensive. It's a state function, just like internal energy, enthalpy, entropy, Helmholtz free energy, etc. So we have here a plot of the Helmholtz free energy against time for a given reaction. So here's our Helmholtz free energy, here's our time. So all these points are the reaction coordinates of this given reaction. Our reaction can exist anywhere along this curve. This is constant volume and temperature. So this can be exothermic or endothermic, it doesn't matter. What's going to happen is the slope is going to get lower and lower. Eventually it's going to level off. So the differential of the Helmholtz free energy is going to be equal to 0 when it reaches equilibrium. So you'll notice that A is being minimized at equilibrium. Now here's a plot of the same sort of idea, except it's the Gibbs free energy function versus time for a given reaction. Again, we have all these reaction coordinates that the reaction can exist at. Starts over here, and as time goes by, the Gibbs free energy goes down and down and down. Remember, this is only true at constant pressure and temperature. So again, it's going to level off. So at equilibrium, the differential of the Gibbs free energy is going to be equal to 0. So you can see by the curve then that the Gibbs free energy is minimized at equilibrium. Now let's talk about entropy and equilibrium. Okay, A, for an isolated system, we're not in material equilibrium. The criterion for equilibrium is the maximization of the system's entropy. Or B, if we have a closed system not in material equilibrium, then the criterion for material equilibrium in a closed system is the maximization of the total entropy. Remember, the total entropy is extensive, so it's the entropy of the system plus the entropy of the surroundings. Now here's the problem though. It's hard to keep track of the surroundings or even control the surroundings. Now remember though that the entropy of the universe is equal to the entropy of the system plus the entropy of the surroundings. Now let's say you have a closed system that starts out at state 1 and it's going to go to state 2. Now let's say it's exothermic reaction, so Q is less than 0, but it's at thermal and mechanical equilibrium. Now it's going through some sort of irreversible change, such as a chemical change or a phase change, but we're saying constant temperature and pressure. So what is this relation between the minimization of the Gibbs free energy and the maximum of the entropy of the universe? Well, we know that the change in the entropy of the surroundings has to be Q reversible divided by T. And T, of course, would be the temperature of the surroundings. And this is true for a reversible isothermal process. We also know that the change in entropy of the surroundings is equal to minus the heat Q of the system divided by temperature. Since by conservation of energy, Q of the system is equal to minus Q of the surroundings. Now, since we're at constant pressure, QP is equal to Q system, which is equal to minus Q surroundings, which is equal to the change in enthalpy. So we have the change in the entropy of the surroundings is equal to minus the change in the enthalpy of the system divided by temperature. See how now we have a relation between what's happening in the surroundings versus what's happening in the system. So we have the change in the entropy of the universe is equal to the change in the entropy of the system plus the change in the entropy of the surroundings. Substituting in, we get that's equal to the change in the entropy of the system minus the change in enthalpy of the system divided by the temperature of the surroundings. Now we're going to factor out a minus 1 over t from the right side here. So we're going to get the change in entropy of the universe is equal to minus 1 over the temperature times this whole quantity of minus temperature times the change in entropy of the system plus the change in enthalpy of the system. That gives us the change in Gibbs free energy of the system is equal to minus temperature times the change in the entropy of the system plus the change in enthalpy of the system. Because we're using delta G is equal to delta H minus T delta S. So now we have the change in entropy of the universe is equal to minus 1 over temperature times the change in the Gibbs free energy. Or just distributing, we get the change delta S of the universe is equal to delta G divided by T. And remember, if it's not specified, we know it's system. So this is delta G of the system. This is only true for closed system. We assumed constant temperature and constant pressure, and the only work is pressure volume work. Now here's a graph showing entropy of the entire universe versus our reaction path. So our reaction can exist anywhere along this curve. So if we're here, it's going to spontaneously go up towards equilibrium with entropy increasing. Or if we're over here, it's still going to spontaneously go up towards equilibrium. So no matter which side you start on, it's going to spontaneously go up to the maximization of equilibrium. Now remember, it's flat on top. Any curve is flat on the top or bottom like this. So that means the differential up there is equal to 0. The differential here is positive and is positive up here. Now, I made a mess here. This is capital S, differential of capital S. So the differential entropy is equal to 0 at equilibrium. And again, I already said these arrows, they're just showing you the direction of a spontaneous process. Spontaneous process is what's going to happen on its own without you having to push it or anything. Here's a similar graph of the Gibbs free energy of the system versus the reaction path. So again, the reaction can be anywhere along here, but if it's over here, it's going to spontaneously go down this way, or if it's over here, it's going to spontaneously go down this way. So it's going towards equilibrium where the G is at a minimum. And of course, since it's flat there, the differential of G is going to be equal to 0. So it's equal to 0 here, it's negative up here, or it's negative up here. And again, these arrows are showing you the direction that a spontaneous process is going to happen. Now, the change in enthalpy is pressure dependent. Now, delta G, the change in Gibbs free energy, is equal to delta H minus T delta S, but only at constant temperature and pressure. Now, we can write these energy functions as functions of other state functions. For example, we write the Helmholtz function as a function of temperature and volume. We write the Gibbs free energy function as a function of temperature and pressure. We write the internal energy as a function of temperature and volume. And we write the enthalpy as a function of temperature and pressure. Now, the change in delta G, it's going to go down, but it could happen because delta H is less than 0, or because delta S is greater than 0. So we could write this like this. Delta H is equal to delta G plus T delta S. So put simply, if we have this change in enthalpy, part of it could be T delta S or TDS, and part of it could be the change in the Gibbs free energy. For example, let's say if we have some sort of gas being burned, the energy is going to be split. Some of that energy is going to become TDS, and some of it is going to become delta G. Now that TDS is basically wasted, but the delta G is useful energy, or it's available to do useful work. Unfortunately, of course, not all the energy is delta G. Now, so delta H, the change in enthalpy, is the total energy released, and delta G is the useful energy released. Now remember, we said the Gibbs free energy is defined as enthalpy minus temperature times entropy. which is equal to U plus PV minus TS. And remember we said the Helmholtz energy is equal to U minus TS, and G therefore is equal to A minus TS. So we have dG is equal to dA plus dPV, or dA plus PdV plus VdP. So dA is less than or equal to minus SDT plus dW. So we're going to, where are we? So we have the differential of U minus TS is less than or equal to minus PdV minus SDT. So now we have dG is less than or equal to minus SDT plus dW plus PdV plus VdP. And so dG is less than or equal to dW plus PdV. So remember, dW has two parts. So far we've only talked about PV work, which is minus PdV, but there can also be non-PV work. So we're going to write dW and then just specify as a subscript non-PV. So that means dG is less than or equal to the dW non-PV. So that means, remember, by our nomenclature, this is work done on the system. So that gives us delta G is less than or equal to minus W. So we're writing minus W just to emphasize now we're talking about work done by the system. In fact, we should probably put a subscript there for surroundings or something to make that clear. So we'll put by. Work by the system non-PV is less than or equal to minus delta G. Now delta G is a fixed quantity for a reaction. That's the sort of thing you can look up. But this work by, this is the maximum possible non-expansion work obtained from any reaction or process or whatever. Now if there is no work non-PV present, then dG is less than or equal to 0 and delta G is less than or equal to 0. So that's PV work only. That's what I meant by no non-PV work. And this of course means reversible, constant temperature, and constant pressure. So for systems with PV work only, then the differential of the non-PV work is equal to 0. Now the differential of Gibbs free energy is less than or equal to 0 if we have PV work only. Now the differential of G is equal to 0 and delta G is equal to 0 if you have a reversible isobaric isothermal process. Now delta G is equal to 0 at equilibrium. Delta G is less than 0 when we're not at equilibrium. And that, of course, will tell us the direction of spontaneous process. And that is the end of section 4.